Hello, and welcome to SandboxAQ's podcast, fAQ, where we talk about all things at the intersection of artificial intelligence and quantum technology, and we do it in a way that's meant for curious humans that aren't necessarily super technical, but we'll try to give an intuitive understanding or intuitive feeling to these different topics. My name is Adam Green, and I'm here today with Tai-Danae Bradley, and we're going to host you on this AQ journey.
Yeah, hi Adam, and hi everyone. Welcome to our next episode. So Adam, today I think we want to get fundamental and down to some basics. On our list of topics today, we're going to talk about bits versus qubits, which hopefully is of interest to folks. Usually if you read any pop sci articles on science these days, you kind of inevitably come across this word qubit. What is that? And how do we even start talking about such a thing? So I think we're going to try to unwind that today. What do you think?
Yeah, no, I think that's a great place to start. And even before we get into qubits, I think you kind of mentioned this. Let's start with bits. So I think that most people probably have a slightly better intuitive understanding of bits. So maybe if we start there and talk a little bit about that word and what that means, then we can kind of roll into qubits. So what comes to your mind, Tai-Danae, when you first think of bits?
Yeah. So typically, I think when you read textbooks or, I don't know, Wikipedia, I haven't looked at the Wikipedia article yet, but usually when folks are explaining this concept of a bit, the story goes, oh, a bit is something that can either be 0 or 1. Or you kind of hear the story that your computer understands things in zeros and ones, like you have to speak to it in the language of zeros and ones. And what are these little atomic elements? These things are called bits. I don't know if that's super satisfactory. You can shrug your shoulders and say, okay, whatever you say. So I think there's a little bit more to the story, but maybe that's kind of the first stab at it.
Yeah, no, I think that's right. Like you think about your computer being full of bits and it's just like this sort of theoretical, esoteric thing, and that a bit is a 0 or a 1. But I don't think that's really the way it goes, right? Like a bit itself isn't constrained to be a 0 or 1, and a 0 or a 1 isn't a bit. But we're talking about sort of like mathematical concepts, physical concepts slamming together and intersecting each other.
Yeah.
So maybe we can kind of dig into that.
Yeah.
Even like the origin of the word bit might be a nice place to start.
Yeah, exactly. And maybe even rewinding a little bit, I feel like maybe we should give some context for why are we even talking about this. I mean, we said we're going to talk about this topic in this episode, but why? So maybe just zooming out like 30,000 foot perspective, if we want to have a podcast on quantum technologies and quantum physics and using those laws at the quantum level and some of the phenomenon to have applications, you kind of need building blocks to work with. Like, what are we working with here? What are our, basic ingredients? And it turns out that at the quantum level, those basic ingredients are called qubits. These are kind of how you store, manipulate, process information. But these have kind of an ordinary analog, which is the thing that we're talking about now, bits. So my laptop is not a quantum computer in the sense that it's used in today's language. I hesitated a little bit because my laptop is, of course, made of molecules and atoms, so that's why I was hesitant a little bit. But the way my computer...
And transistors are quantum devices in some ways.
Yeah.
So the lines get a little bit murky for sure.
That's right. It's all quantum anyway. Okay, but if we really want to kind of dig into the fundamentals on the classical side of things, how information is transmitted in my video and your video and these sound waves and all of this stuff is processed through our computer using these things called bits. And as you mentioned, you can kind of think of, I guess one thing that I think is helpful when first learning this concept is that there's kind of the concept or the idea of a piece of information that folks call a bit. And then there are also different ways to physically represent that concept. And sometimes when folks are having conversations, whether with actual people or through an article or something, they may use the word interchangeably for either the abstract concept or the physical instantiation of that thing. So maybe we want to be a little bit careful and say that for the first few minutes of this conversation, we probably are talking about what is a bit or a piece of information just from a conceptual viewpoint? How are scientists referring to it? What is the idea that they have in mind? And then maybe in a few minutes in this conversation, we can give some examples of physical ways to represent this abstract concept called a bit. So that's kind of
I think
maybe,
that's I think that's great.
yeah,
Yeah, and I think that's the stepping stone, right? Like first we talk about bits in the classical sense, and then we can talk about bits in the quantum sense called qubits. So we're kind
yeah,
of laying that foundation. We'll move through
yeah,
that, and then start talking about qubits and some of the special things that
yeah,
kind of come along with qubits that give quantum computing and quantum devices their power. So I think
yeah.
this is a great place to start.
Excellent. So you mentioned something about etymology. So what is a bit? It's spelled B-I-T. It's like a little bit of information. Oh, a little bit of information. Is that where the word came from? No, not quite, but I think it's pretty good. um, so I was doing a little bit of reading in preparation for today's episode, and it turns out that, as far as I can tell from the literature, the word bit was first made an appearance in a 1948 article by a mathematician called Claude Shannon. Claude Shannon is known as the father of information theory. Information theory, the study of information, how it's communicated or conveyed. And in this paper on page 1 in 1948, he credits another mathematician, John Tukey, for
Mm-hmm.
coining this word bit, which is a combination of two words, binary and digit. And in this paper, Shannon says that a bit, we're going to define it to be a unit of information. A unit of information. So if I tell you something, I give you some sentence, it could be meaningless or it could have a lot of meaning. So you can kind of measure, oh, how helpful was this thing that I just told you? You know,
Mm-hmm.
if if we're in California, if we're in Southern California, and I'm like, Adam, it's sunshiny today. You're like, tell me what else is new. Like, it's always sunshiny in LA. Like, I know that, you know? So there's not many bits. There's not a lot of information in that. But if I tell you something, Adam, there was a blizzard in LA today. Can you believe it? Wow. That's a lot of information, you know? That's actually, there's something there. So that's kind of how much information is being conveyed. But what do you measure it in? You know, do you measure it in feet? No. Do you measure it in pounds? No. What do you measure it in? So the answer now, a la Shannon in 1948, is something called a bit. Um, and it's really something defined in terms of the logarithm function, but maybe that's another story for another day. But if folks are interested, you can read page 1 of this paper. I think you can find it online free. And he kind of describes the intuition behind why this thing called a bit that's measured in terms of this mathematical function called log is actually valuable. But then when you kind of, you know, get down to the basics, um, it turns out that kind of working with two fundamental measures of information, like if I tell you a statement, you could ask me, is that true or false? Like, is it sunny today? Is that valuable or not valuable? Is that true or false? Well, I guess it's true. It's always sunny. No big deal. Um, but if it's blizzarding, is that a true statement or is that a false statement? Well, I don't know. Probably the likelihood is it's not true. So when you have this dichotomy between measuring the or evaluating the veracity of some statement, and really it's a question of logic historically, you come down to two fundamental answers, yes or no, true and false. But maybe for brevity, we don't want to always write down the TRUE, blah, blah, blah. So eventually it's just easier to say, look, just every time you see option A, write a 0. Every time you see option B, write a 1. So when people are talking about bits, I think it's this idea of true or false, yes or no. I'm evaluating statements or sentences or something that's being communicated. Is that true? If this happens, then I do this. You have kind of these two options. Of course, you could have more. Why not have 10 options or 13 or whatever, or continuum? And those have names too. instead of bits, they have other names. But it turns out, I guess, 2 is a pretty easy number to work with. So what do you think?
And those can be
Did you?
represented. Yeah. No,
Yeah.
I think I'm following. Like, I mean, the idea of a bit in terms of describing the amount of information or how much information is in a statement, it kind of feels like a normalizing factor.
Mm-hmm.
And that and correct me if I'm wrong here, but like in our modern interpretation, when we have strings of bits, like that's information that's getting passed
Yeah.
through your computer, through the internet, et cetera. And you usually hear these kind of increments of like 32, 64, 128, all of these like sort of series. And that refers to the amount of information that's in that packet or that's being transmitted. And so that's just the number of bits. And I think you're getting at this like binary piece of it that's usually kind of depicted as being a 0 or a 1 or on or off. And I think that that's starting to get us from the theoretical idea of what is a bit to the sort of practical application of like, okay, what is a bit in real life then, if we're talking about the sort
Yeah.
of theoretical piece of information and asking questions and the value of that information that's in there. Like how can we like best think about bits in a concrete, like physical form?
Yeah. I think usually, I mean, the first answer that people might give, especially in the context of this discussion, are things like current passing through a wire, or
Mm-hmm.
transistors. I want to say for the record, though, um, there's this really great book called The Pattern in the Stone, I believe, by Daniel Hillis. I highly recommend this book. It's basically describing how computers work. And if that sounds boring, I don't know, maybe that sounds exciting or boring, but don't think of it as your typical, here's a hard drive, here's what software means. It's not that. I love how this author really breaks down how computers work and just the fundamental ideas that make it tick. And as you kind of have hinted at, a bit is fundamental to that. Why do I bring this up? Because you ask kind of examples of physical instantiations of this concept called a bit. A wire, a wire with current flowing or not flowing, that's a kind of a typical example. But you can have another channel through which something is flowing, and that's perfectly good as well, like a pipe. I can have a pipe with water flowing. Is the water flowing? Oh no, that's a 0. It's a representation of a 0. Is the water flowing? Yes. Oh, that's a representation of a 1. You can build a lot of other things, and I love this book because there's a lot of examples of that. I can actually build, a computer made out of water pipes that can do everything that my laptop is doing right now. But, this will just be really massive and not practical. But I just mentioned that because there's nothing conceptually, I guess, unique about current and wires. It's just anytime you have something that kind of has 2 states, a yes or a no. Of course, if you want to be practical and do things that are manageable and that you can carry around with you, then you want to be, have size considerations. But what I really like about this book is that it kind of says, like, physical instantiations aside, here are the fundamental ideas that kind of make computation work. And it's just written in a really wonderful, accessible, friendly way. So that just reminded me. I wanted to share that with folks.
Yeah, no, thank you. Sometimes I think it's really helpful to take a step back and instead of really focusing in on wires in the computer, you're kind of like getting ahead of yourself a little bit. And when you back up a little bit and think that, yes, it works that way, but can work other ways too. It can kind of expand your mind a little bit, and you can think about things in a little bit of a different way, and then reapply that knowledge to the question at hand of bits in a computer. So no, thanks. I think that's cool. I haven't read that book, but I should check it out. We'll put
It's
it in the
very
notes.
good. It's very good. Yeah. So one thing though about, I mean, folks may wonder, okay, what's the connection between this and then our other topic of the day, which relates to the quantum world. Um, One thing that I think is helpful when thinking about how computation works, you're taking something, whether it's letters in the alphabet or, colors in the color spectrum or something, and you're translating them into language that's readable by your computer. So zeros and ones, or strings of zeros and ones and bits. And then maybe you want to do something to that information, like store it somewhere, or send it to someone or manipulate it somehow to get new information back. So essentially you have is like a function or like a little machine. So you input a string, it does something to the string, and then you output a new string. So you input information, you do something, that's a function, and then you output it. But then, the question becomes, well, what if I have several strings and I want to do the same kind of manipulation to them? Well, I have to either, multiply the time that it takes me to do this. I did it for string 1, now I do it for string 2, now I do it for string 3. So now you're taking up a lot of time if you kind of run the process sequentially. Or you could try to maybe do it in parallel. So you multiply the hardware that you have so that it just does it in, parallel on each of the strings. So in either way, if you have a lot of information, it either costs you more time or, more money, so to speak, like more hardware to get the thing done. And so this is kind of now inching us to this quantum advantage or, this new type of way to encode or store information, because it turns out that this thing called a qubit, which we may get to in a second, sort of alleviates some of that because they're just very different. And so I just kind of wanted to throw that in there so that folks can maybe see the context of this. So you have these bit strings, and this is how computers process information. But the point of computation is you want to manipulate them somehow to give new helpful information. So you have to think about the time that it takes to do those manipulations. Now imagine if you have a whole bunch of things, right?
Yeah, no, I think that's an important application piece to all of this. And that gets into the practical pieces of when you're shopping for a computer, or you look at the little about screen on your computer and you see some kind of gigahertz clock speed, and how many cores you have in your CPU, your central processing unit. And that clock speed is like a reference to the parallel or to the sequential piece that you were just talking about, with how many of those manipulations can happen within that core CPU each second. So it's going to be millions or billions, like these gigahertz numbers. That's how many cycles you can do in 1 second. So that's how many of those manipulations you can do. And if you have a quad core machine or something like that, then you have 4 different cores that are all working at that clock speed. So then you're getting into the parallel piece a little bit. And supercomputers these days just take lots of cores, lots of CPUs, and they're running a lot of parallel processes. So that's how you can get speed ups with classical computers. But to your point, I think a lot of people usually hear about quantum computers and hear about these huge exponential speed ups or quadratic speed ups that they can have over classical computers. And that gets us into qubits and what makes qubits special. So I think that's a great transition into talking a little bit more about qubits. So we've been talking a lot about bits and how bits are sort of used in computing in classical computers. Let's talk a little bit more about qubits now, and maybe we can talk about how qubits are similar in some ways to bits and how they're different. What do you think?
Yeah, I think that's a great idea, great plan. So what are these things called qubits? And maybe we can start by what you said. How are they at least similar to bits? So I would say, just like a bit, a qubit has both a conceptual or abstract sort of definition or way of thinking about it. And that concept also has a concrete physical representation, or many. There are sort of types of qubits, just like there are types of bits. You can have, I think we mentioned water flowing through a pipe. That's like a representation of a bit, or not flowing. Or if you replace the water by current, flow of electrons, that's another example of a physical bit. So just in that way, qubits have physical examples, but they also have sort of a conceptual understanding. So maybe let's talk about the concept of a qubit first, and even how that's similar to a bit. So one thing we mentioned is that, oh yeah, go ahead, Adam, go ahead.
Yeah, no, let's definitely get into that. I was just thinking, we went through sort of the etymology of bits with binary digits. Yeah. So maybe before we even get going into the sort of conceptual piece of qubits, let's dig into that word. Although it might be obvious to some people that are watching, it's interesting to me because bit itself is this thing of binary digit. And then now we're in the quantum realm. So we're just kind of slamming quantum onto the front of this thing that's already been sort of shortened to mean binary digit. Now we have qubit, which is just Q on top of the bit for quantum bit or quantum binary digit, but things start to like fall apart. I think when if you go back too far, I'm not sure that I would think about qubits as quantum binary digits, but that might be a good place for us to start when we're talking about the conceptual piece, because in some ways, like you mentioned, qubits are similar to bits where they can have that sort of similar representation.
Yeah.
So,
that's a great point. And I'm so glad you brought that up. And maybe just for even more clarity, if folks are wondering, qubit is spelled Qubit, not like Q-bit. So it's not like Q-tips, but it's a qubit. Did you know? Okay, so a qubit, like a bit, could be thought of as like a unit of information. Like bits are carrying information and qubits are kind of doing something similar. So speaking of units, did you know that there's another word called qubit spelled C-U-B-I-T? Have you heard of C-U-B-I-T before?
Oh, like, is that like Egyptian? Or,
yeah. It's like an old...
like measurements?
Yeah, exactly. It's like an old-timey way of measuring things. I think it's like equivalent to 18 inches or something. So when we say qubit, we don't mean that one. Although that is also a measure of something. It's like a unit of something. But instead of measuring length, we're now measuring information, basically. So I thought that was a fun fact. So it's Qubit.
That's a good one. Yeah.
Yeah. Okay, so that's kind of how, great point about the etymology and how that's kind of similar to bits. So quantum bits. What's another similarity? Yeah, it's a measure of information. Like bits, qubits can also sort of represent or carry information that comes in two flavors, like yes or no, true or false, or 0 and 1. But it's that and more. Okay, so how do we get to the and more part? Okay, here's one thing I did. So in preparing for this episode, I made some notes to myself, and I thought, okay, how would I try to explain what I think a qubit is in really basic language? So I actually wrote it down, and I'm going to read this because I can't just remember what I said a while ago. So I'm going to read what I wrote, and I want to know if you think that this is helpful, or you're like, that's horrible, let's like help her out, okay?
No, this is great. And this is the first time I'm hearing this, so this is great.
Yeah, exactly. Okay, so I wrote to myself, I think a quantum bit is easy to explain. I'm sorry for the hubris there. I think a quantum bit is easy to explain. You find some physical object that happens to be really tiny, that has two stable positions. Okay, when I say two stable positions, that's actually a phrase that was used in Claude Shannon's original paper on information theory, where he was the first person to introduce the word bit. So I'm just kind of borrowing from him. We mentioned that paper earlier. But anyway, you find a physical object that happens to be really tiny, that has two stable positions, or like two states or two options that you can find it in. But then you realize that you can't just flick it on with certainty. So it's not like a light switch where if I know I flick it up, it's on, and if I flick it down, it's off. Like I know that with certainty, but that doesn't quite happen when you work with really tiny objects. The thing, or this tiny object, may actually have an affinity for one of those two positions, meaning it might be more likely to be found in one of those two positions, or, in one over the other. So I have put in cursive, so this is all in print, but in cursive, I wrote the word found, and then I underlined it. So I think what I'm trying to emphasize to myself is that a qubit is not something that you really have a whole lot of control over, meaning it's not a kind of deterministic thing. That's the word that people use. But it's more of probabilistic or statistical. So this thing has two states, and you're kind of the recipient to whatever's going on with this thing. And maybe it can be in one of those two states, but with some probability you will find that it's in state 1 or in state 2, rather than something that you can kind of just go in and force with certainty. So, and then I finished by saying such objects with this property are found at the quantum level, ergo they are called qubits. So that was kind of a mouthful, but that was my sort of roundabout way of trying to think of this concept and explain it with some clarity. But maybe I completely failed. I don't know. How did you feel about that?
No, I like it. I like it. I think that drawing that connection between bits and qubits, that's what I was doing in my head when you were talking, because I think we were talking about bits having those two states or two positions, but that you use the word deterministic. Right. So I think another way to think about that is that they're, I don't know about easier to manipulate, but they are more straightforwardly manipulated, or that even if that's not true, their state, like, are they a 1 or are they a 0? Like, that's a little bit more straightforward at the bit level of you have a 1 or a 0, then you said, but there's something else with qubits. So I think that like connection is made really nicely, that we're even in a qubit, we're looking for something, or a good qubit has those two possibilities, but how the qubit is oriented in one of those possibilities is where things start to deviate from bit land when you're in qubit land. And then there's also that piece of like, it should be really small. And I think that that's not something that we probably will go into too deeply, but also not something to gloss over, that there is these quantum properties of things that happen to be very small. And that's where those properties are most easily seen, or can be measured by humans. Like the world is a quantum world, but you don't really see these quantum effects so much at the macro level, but you do see them. They have a bigger impact at the sort of micro, very, very, very small level. So that's kind of what I'm getting out of your definition, which I like, is that there's a lot of similarities to bits, but there are these differences that come when you start to try to manipulate them, because it sounds like they almost have like a little mind of their own, where they tend to want to be in one state, maybe more than another state, or there's some probability, and that probability isn't necessarily just 50-50 right off the bat, like what you might say with a fair coin, or electricity moving through a wire or something like that. Does that make sense?
Yeah, I know. That's great. That's great. So you mentioned, a coin or a wire, but maybe now that we've kind of discussed from a high level perspective this new concept of a bit, folks might want something tangible to grasp, like, okay, when you guys say qubits, like, what should I have in mind? And you mentioned something really tiny, but what exactly? So maybe we should now talk about some physical examples of qubits, and maybe as we do that might help hone in this concept even more, because I think it's not totally intuitive, what we're talking about. We're talking about something we can't even see, so that's pretty difficult. So I'm just giving folks a disclaimer, this is kind of difficult, so maybe the first pass is not clear, but on the second pass now, what are some physical examples of qubits that maybe can help make these ideas even more concrete that we're talking about?
Yeah, no, I think it's a good push. There's two that come to my mind at first that might be like nice introductions. There's a whole bunch more than just two, but there's two that I like to usually think of. One of them is a photon, and one is an electron. So I think that kind of ironically, since you said that they're hard to see, like, I guess photons themselves are difficult to see maybe one-on-one, but, photons, so a little packet of light, essentially. Yeah. And that is something that can be used as a qubit that has different states based on the orientation of that little wave or packet of light that's traveling through some kind of medium, or even a vacuum. And the different sort of polarizations, or the different directions that wave is propagating in, can be used as a qubit. So the qubit is the photon, and a qubit also is sort of like, I think about it as like a property, like the actual measurement piece of the photon has to do with its orientation. So like the physical manifestation, or what we're actually would be measuring, isn't necessarily the presence or absence of a photon. It's some aspect or characteristic of that photon in how it's actually oriented. And that is where the information is carried in that orientation of the photon, for example.
As you were talking, I was also thinking, so I'm a mathematician, as you know, and I am used to working with a piece of paper and a pencil. I am not used to working in a lab with equipment and so forth and so on. So the more I learn about this stuff, I just want to say, I think that the engineering behind all of this is remarkable. I mean, can we just appreciate the fact that people are doing things to particles of light? It's not like a thing people do, but actually they do. It's really incredible. I think the technique and the technology to manipulate these teeny tiny things that are not visible to the naked eye. And you also mentioned electrons.
Yeah.
It's just, I don't even know what to say at this point. I'm just very, very impressed as I've been reading some sort of more engineering physics papers recently, and it's just kind of mind-blowing how advanced technology is and the ideas that engineers have to build machinery that allow us to probe this subatomic world. I mean, wow. Anyway, Okay, I just had a moment.
No, you're right. Yeah, and there's so many like more challenges that need to be surmounted in order to really bring at least quantum computing into its kind of heyday. But there are other things that you can use qubits for besides quantum computing. But yeah, when you see these quantum computers, these chandeliers that are cooled down to colder temperatures than what you see in outer space in order to move these electrons around in a way that can be controlled and used in a quantum computation, it's mind-boggling to me. It's just like fantastic and amazing. And then also amazing to think that there's so much more to go before we can get like truly functional quantum computers and even some quantum sensors. It's a wild time.
Yeah, it is. But I want to let's camp there for a second, because you mentioned quantum computers and you mentioned how qubits are sort of used in that application, and a particular kind of qubit that folks may or may not have heard of in this context is superconducting qubits. And I know that you have a really nice way of thinking about them. So do you think that you could take a stab at describing what a superconducting qubit is and sort of how that's relevant to the world of quantum computing?
I'll give it a shot. I'm far from an expert in these things. I think we're both kind of learning this stuff together. But yeah, I mean, I think that the way that I understand it is, superconducting material or superconducting qubit or superconducting quantum computer. The superconducting part essentially means that there's no resistance when electricity is passed through a circuit. And generally, but not always, generally things have to be really cold in order for superconducting material to actually have that capacity. And that's essential for superconducting qubits, is to have zero resistance in their circuit. And at its core, my understanding of a superconducting qubit is it's essentially a chip. It's an etched microchip or something similar to a microchip that has electrons that can flow in pathways through that chip. And in the way that electrons are moving through that chip and the way that they're measured and manipulated allows aspects of the electron to be measured and used as a qubit. So that's my general understanding. I think that's very high level understanding of how we can use that circuitry that we kind of know a little bit about from decades of building computer chips and things like that, but used in a different way in order to be able to shuffle these electrons around and use them as qubits in certain points on the chips.
Yeah, that's amazing. That's amazing. So to just kind of recap, one example of a qubit is a photon or a particle of light, and such particles have different properties or aspects, which we won't get into. But those different properties or aspects or orientations, as you mentioned, can serve as encoding information. Like if my particle is doing option A, that's a little bit of information. Or if it's doing option B, that's a different piece of information. Another example, what you just gave, is the superconducting qubit, which maybe we should have, a separate conversation. We could just probably spend 30-minute episode talking about that itself. But you have a chip with electrons flowing through it, and that configuration can also have certain aspects or properties to it. So that's another way that you can encode information. Mm-hmm. But I think you mentioned that qubits are used in quantum computing, but also in other applications. So maybe that could be interesting. I don't know if you had this one in mind, but when you said that, I was thinking of medical imaging and medical sensing applications. And I know that we've both talked about a really nice qubit in that context. Are you reading my mind? Do you know which one I'm thinking of?
I might be, but why don't you go ahead and talk? Is it the shiny one?
It is the shiny one. Yeah, that's right. So there's another kind of qubit called an NV center, or a nitrogen vacancy center, which can be used. I think you can kind of craft this in the lab in different solid state materials. One happens to be diamonds. So folks can create something called a nitrogen vacancy center in diamond material. So that's really cool. So whenever you look at your diamond ring or something, or diamond earrings, think about qubits. Okay, how does this work? Well, I am no expert, but my understanding is that in a diamond, you have a lattice of carbon atoms. And you have all of these carbon atoms, and they're kind of connected to one another in this structure, in this lattice structure. And what one can do, not me, but what other people can do, which I think is really amazing, is can you remind me how this goes? You take out a carbon atom.
Yeah. Essentially, you replace a carbon atom with a nitrogen atom. Yep, and so you're interrupting that lattice.
Yes.
And then, the details are a little bit beyond me, but essentially in doing that, you change the bonding structure of that part of the lattice, and you create what's called a vacancy, which is a spot, like an open spot where there used to be a carbon. Yeah, now it's a space, and that space can interact with the electrons, I believe, on the nitrogens and on the surrounding carbons, and then that vacancy, or that nitrogen vacancy center, has properties of a qubit.
Yeah. Okay, that's incredible. But folks could wonder, I wonder, how do you know this has properties? First of all, we should get an expert on. I'm thinking, who figured this out? Was this an accident? Did someone sneeze or something? And they're like, oh, qubit. Who? I'm sure not. I'm sure it was much more intelligent than that. But I just really think this is fascinating. So one thing you may wonder is, like, how do you know this is a qubit? How do you know that you can use this to detect or to measure something? You do this shenanigans inside of your lattice, and how does something useful come out? And I think the answer is kind of something that's used in all of these cases, which are lasers. So you can use lasers to manipulate things at a very small scale. And from what I understand from kind of a high level perspective is that if you have one of these NV centers and you want to know what state is it in, this represents a qubit, so it must have two options. How do I know which of those two options are going on at this time, or at a given time? So you can shine a laser on this thing, and depending on sort of the light that you get, so you're shining light into your qubit, and out from that comes another little ray of light. And depending on the intensity of that light, it may be very bright or it may be very dim. That clues you in onto the state of the qubit represented by this NV center. And I think that's really amazing. So even though we cannot see this very teeny tiny subatomic little universe, we can still use things we can see, like lasers, to clue us in to what's going on into the world that we can't see. So I don't know, it's like, this is not a good analogy, but it's like going to the movies and you put your 3D glasses on. You couldn't see some stuff, but you view it in a certain way, and all of a sudden, like, your eyes are open into this invisible world. So I think that's really interesting, and that kind of gets into how do you measure these things, which we mentioned earlier. So I guess one way of measuring a qubit in this example is shining a particular laser on it and seeing what you get from that.
That's right. Yeah, there's an interaction between the laser and the NV center. And folks might be wondering, okay, well, how are you going to build a computer out of that? And you might be able to build a computer out of that. But I think that's like a really nice segue into that qubits are not just about quantum computing. So you can use qubits like these superconducting qubits to do quantum computations, and we'll talk more about that in a future episode. But you're not always like restricted to using qubits in computing. This NV center that you were just talking about is actually used in sensing more often than computing, as far as I know, because what happens is that NV center is sensitive to things in the environment. For example, like magnetic fields, and magnetic fields will also have an effect and manipulate what's going on to the state of that quantumness, the quantum state of that NV center. And then you can use that laser that you talked about to probe the qubit, to probe the state of the qubit, which is related to its environment. So as a magnetic field changes, the qubit changes, and then the intensity of light that's being emitted by that qubit when you shine a laser on it also changes. So it's like one thing stacked up to another thing, stacked up to another thing, that like down the road, you can then see what's going on in the environment. And these little NV centers, and there can be billions of them in a diamond. You can have just one, or you can have literally billions in a diamond. Those are really, really, really sensitive. And actually they turn out to be great magnetometers. So you can really tell a lot about the magnetic field in that area by measuring the qubits and the way that they've interacted with the magnetic field by using the laser and sensing the light that's coming off the laser is related to the magnetic field. So that's a very non-quantum computing use case for qubits, where you actually want that environmental interaction in order to be able to tell what's going on.
Yeah. Okay. So that's a great point, because one thing that we haven't really mentioned, although you just hinted at it, is that qubits can be very fragile and sort of sensitive to the environment, or delicate to the environment around them. One could think that that's not a good thing. Like, oh no, I want something that's more robust. But actually, you've just described a use case where that sensitivity is desired. Like, this is a good thing. So maybe you've seen something that seems like a negative, but actually you've turned it into a positive in the philosophical sense, not the scientific sense.
It's a feature, not a bug. Yeah, I mean, we were talking about those superconducting quantum computers. The reason why we keep them so cold and so shielded and everything like that, and they have all this shielding around the actual quantum computer chandelier. You may have seen pictures of these things. They look like brass and gold, and then they have all these containers in them, these refrigerators. It's massive, all the stuff that's in there. One of the main points of doing all that is to shield those qubits from interactions with the environment, because if they're so sensitive that an environmental interaction will sort of ruin that qubit for quantum computation. Like, we want to be the ones to manipulate the qubits, like very, very specifically. That's like flip that on its head when it comes to things like quantum sensing, where we want to like throw that qubit out into the environment and let the environment do all of the changing, and then we can measure those changes and get some information about the environment. So the sensitivity piece is a feature to those. So it's just like with bits or with other things, context matters. And depending on what you're trying to use them for, there are different attributes that you might want to use. A superconducting qubit is probably not going to be great for measuring environmental change, but this NV center is great at doing that, but might not be the best fit for trying to do computation with.
Yeah, that's an excellent point. So if folks are like, why are there so many different examples of qubits? That's the answer. There are different examples of qubits because different folks may have different applications in mind. And so I think what companies are doing is they're focusing on honing in these qubits depending on what application that they have in mind specifically, like weighing strengths and weaknesses and then pairing that to the use case. So there are other examples of qubits besides the few that we've talked about. Probably we won't chat about them, but maybe we could just say a few for the sake of completeness. So another one that comes to mind are like trapped ion qubits. There's these things called neutral atoms, quantum dots, topological qubits, like a whole array of different flavors. But that's kind of why. So if it feels overwhelming, just remember, I guess for folks, there are different applications, and some are sensitive just like the ones you mentioned, which is a good thing, but not in all cases. So you want to choose accordingly.
Yeah, no, I think that's a great point, and we'll have some resources coming up on those different types of qubits if folks are interested. And I think that as you sort of mentioned a bunch of those different types, when we hear about ions and atoms and heard about photons and electrons, it's interesting for me to think about, like, how do you make qubits? How do you prepare qubits? Like, do you go to the qubit store and and pick up a bunch of qubits, like you might go to a store and pick up a bunch of wire to build a computer or other components and things? And at its fundamental level, like, the way that I like to think about qubits is mostly they're sort of quote unquote natural, like nature creates them, and then humans manipulate their features in order to do whatever they want to do with them, whether it's sensing or computing or other things. But when you're talking about photons, we can make photons by turning on a light switch or turning on a laser, and then nature sort of takes care of the rest. If we're looking at electrons, it's similar. If we're looking at ions or atoms, like, these things are produced by nature, and then the job of the quantum engineer is to figure out a way to manipulate the certain aspects of those of those things, those atoms, those electrons, those photons, in a way that we can use them for either computation or sensing or something else. So the qubits themselves are sort of provided to us in most cases, and then it's more about being able to control them very, very, very finely, which is a huge engineering challenge, to try to manipulate the attributes of an ion or the attributes of a photon in a very predictable, consistent way in order to be able to do these types of calculations with them. So it's just something that I like to kind of think about, that, like, qubits just kind of come as is, and then it's up to the engineers to figure out how to really use them for these different purposes.
Yeah, that's remarkable, I think. And that, I think it's a similar story for basically all of quantum technology, which is harnessing or making use of the laws that exist in nature at the quantum level. So it's not like someone was like, oh, I think I would like these little things to have this property called entanglement. Let me go cook up some entanglement in my kitchen. No, it's just there, And then along the way, folks are figuring out ways to use such thing that exists already. I think that's pretty incredible.
Yeah. Yeah, no, I think that's amazing. And that might be a good place for us to kind of wrap up, because I think we're starting to bump up against some of those properties that really make qubits useful. We've talked a little bit about some of those in kind of a high level. And I think maybe in our next episode, we can dig deeper into what we're actually talking about with this kind of, qubits are like a bit, but more. Right. So we've been kind of hunting around that a little bit, and maybe next time we'll dig into the and more part. What do you think?
I think that sounds great. So maybe just to kind of give folks a peek into what that is, it has a name. I think I know what you're talking about. Superposition. Yeah.
That's right.
So what is that? Well, tune in next time and we'll chat about that.